All right. Hello for everybody tuning in. Today we're picking up where we left off yesterday. Um, so we were talking about the blow up of a variety, um, where basically the blow up of AN ends up being the diagonal subset of AN across Pn minus 1. And what that looks like geometrically is taking, your curve where like if it's hold on. There's a name for this type. If there's a node, then we can blow it up into the picture on the left. So this on the right is called a node. We can blow up a node into this thing on the left through phi, basically by attaching a tangent bundle at 0. And so now what we want to do is we want to study the properties of the blow up at x. So properties of BL0 and equals x. It's a notation thing. This means injective morphism. So just general terminology in commutative diagrams. This type of arrow, well, like that, is injective. This type of arrow is surjective. And then this is bijective. Okay. Let P be a point in affine n space, non-zero. And phi inverse of P is equal to a singleton set. And then phi also gives an isomorphism of x without the inverse of our blowup onto an minus 0. Basically, the point at which we blow things up is isomorphic. The point at which we blow things up becomes this tangent bundle of projective space. And so if we remove that point, then our spaces are equivalent. So for example, let P be A1 through AN, with some AI non-zero. Then P Cartesian product Y1, Y2, Yn, and phi inverse of P then for each j, yj is equal to aj for ai yi. This is kind of our homogenizing factor. Which makes the yj coordinates homogeneous. So y1 through yn is uniquely determined as a point p-1. In fact, we can let y1 through yn exactly equal p. So phi inverse of p consists of a single point. So any questions on this construction?
No.
Okay. So to finish up the isomorphism, for every point in an without 0, setting psi of p is equal to p cross p, defines an inverse morphism. Excuse me. To psi, or to phi. So is this construction clear and like what our claims were? This was claim 1. And then this is claim 2. One, two. So our second construction is phi inverse of 0 is isomorphic to Pn minus 1. And this is by setup. This is just how we defined it to work. So our picture here is really, I guess, in retrospect, I maybe should not have used orange there. There we go. And this is that makes sense. So then that is not a word. So does this make sense that the set of points in phi inverse of 0, which are isomorphic to Pn, kind of have to be in one-to-one correspondence with the set of lines through 0 and An? And if not, let's build that out. Okay. Let's see. So our final construction is that the blow up at 0 of An is irreducible. So in this way, we have yet another variety. And so kind of the proof here is that X, which is the blow up at 0 of An, is the union that's literally just of X minus phi inverse of 0 union phi inverse of 0. But this first piece is isomorphic to An minus 0. And then this is Oh, not dense. This is some subset of A1 contained in n minus 0 by our covering theorem. And so then x minus psi, or phi inverse of 0 is dense in X. And X is irreducible. Essentially, this is the closure of like x minus phi inverse of 0 closure is equal to x minus phi inverse of 0 union phi inverse of 0 is equal to x. So do all of these constructions make sense about like how this works, what the structure is, how we use this in a practical way?
I'm not sure how to use them in a practical way.
Good. Okay. Houston, we have liftoff. Okay, so here's how this becomes useful. So we want to, the whole premise, and I'm just going to start reading from chapter 1.8 about the premise of algebraic geometry, or classical algebraic geometry. Okay, so keep in mind that there's still, I guess, 2 sections left that we haven't done. Now that we've met some algebraic varieties and have encountered some of the main concepts about them, it is appropriate to ask, what is the subject all about? What are important problems in the field and where is it going? To define algebraic geometry, we could say that it is the study of solutions of systems of polynomial equations in an affine or projective n-space. In other words, it's the study of algebraic varieties. In any branch of mathematics, there are usually guiding problems which are so difficult that one never expects to solve them completely, yet which provide stimulus for a great amount of work and which serve as yardsticks for measuring progress in the field. In algebraic geometry, such a problem is the classification problem. In its strongest form, the problem is to classify all varieties up to isomorphism. We can divide the problem into parts. The first part is to classify varieties up to birational equivalence, which you are all now familiar with. As we have seen, this is equivalent to the question of classifying function fields up to over K up to isomorphism. The second part is to identify a good subset of a birational equivalence class, such as non-singular projective varieties, which we have yet to talk about, and classify them up to isomorphism. The third part is to study how far an arbitrary variety is from one of the good ones that you've considered above. In particular, we want to know, A, how much do you have to add to a non-projective variety to get a projective variety, and B, what is the structure of singularities and how can they be resolved to give a non-singular variety? Typically, the answer to any classification problem in algebraic geometry consists of a discrete part and a continuous part. So we can rephrase the problem as follows. Define numerical invariance and continuous invariance of algebraic geometry, like K of x, O of x, and local rings. They're all invariants. Which allow one to distinguish among non-isomorphic varieties. Another special feature of the classification problem is that often when there is a continuous family of non-isomorphic objects, the parameter space can itself be given the structure of an algebraic variety. This is a very powerful method because all of the techniques of the subject can be applied to study the parameter space as well as to the original varieties. Let us illustrate these ideas by describing what is known about the classification of algebraic curves over a fixed algebraically closed field K. First, the birational classification. There is an invariant called the genus of a curve, which is a birational invariant, and which takes on all non-negative values g greater than 0, or greater than or equal to 0. For g equals 0, there is exactly one birational equivalence class, namely that of the rational curves. And then for each g greater than 0, there is a continuous family of birational equivalence classes which can be parameterized by an irreducible algebraic variety M subscript g called the variety of moduli of curves of genus g, which has dimension 1 if g equals 1, and dimension 3g minus 3 if g is greater than or equal to 2. Curves with genus 1 are called elliptic curves and have been the study of basically all of modern math and modern arithmetic algebraic geometry was elliptic curves. And as a brief aside, something I'm planning to do over winter break is I went and I got the proof of Fermat's last theorem printed out and bound. So have we talked about Fermat's last theorem at all?
I believe so.
Okay, so basically Fermat's last theorem says, you know your Pythagorean triples?
Yeah.
Yeah. So the idea is for any equation x to the n plus y to the n equals z to the n, for n greater than 2, there are no integer solutions to that equation. And so Fermat wrote in a textbook that he basically would send out like problems to his friends, but he would put them all into a book and then send the book of problems to his friends to think about. And so he said, when he wrote down this problem, I have a proof, but I can't fit it in the margin here, but I promise I have one. And then he died. And so it was kind of a large focus of math in like the early 1960s, and obviously like people cared about it, but like really it's not one of the, it's kind of like the twin primes conjecture, the Collatz conjecture. I don't even know if I'm saying that right. Collatz conjecture, maybe? I don't know. Nowadays it's like the three of us aren't really thinking about it. Everybody's kind of like, oh, it's going to be an unsolved problem, maybe somebody's going to do it someday. But you know, basically this guy Andrew Wiles picked it up because there's a great documentary about it. So there was this one paper that basically said, okay, if Fermat's last theorem isn't true, and we can find integer solutions for n greater than 2, we can make a really weird elliptic curve that has some strange properties. And in this way, that paper was able to actually connect these things called elliptic curves, which we talked about briefly over the summer, by the way. And so they were the things we dealt with in elliptic curve cryptography that are equations of the form y squared is equal to x cubed plus ax plus b, or at least that was what we looked at. Sometimes you can add an x squared term in there. It doesn't really matter. And which yield something that looks like this. Or can yield something which looks, hold on, I didn't do that symmetric enough. Like this. So there are really two specific types of elliptic curves in this kind of visualization way, and they depend on the coefficients. But basically, Andrew Wiles said, okay, well, we've connected this idea of elliptic curves to Fermat's last theorem. There ended up being another proof and really a conjecture that every elliptic curve has this thing called a modular form. And by a long string of logical implications, it ended up becoming Wiles's idea that if he could show that every elliptic curve has a modular form, then he would have proved Fermat's last theorem. And that's exactly what he did. And so he was an arithmetic algebraic geometer, meaning he considers the algebraic geometry of arithmetic functions. And And so yeah, that proof took like 8 years. We have some people in our math department who were kind of connected to it at the time. So yeah. So anyway, curves with genus 1 are called elliptic curves. Thus, for curves, the birational classification question is answered by giving the genus, which is a discrete invariant, and a point on the variety of moduli, which is a continuous invariant. So this is covered more in chapter 4, he says, which is on curves, looking at the Riemann-Roche theorem and Serre duality. We use very little of the fancy methods of schemes in cohomology. You can read this chapter at a much earlier stage of the study of algebraic geometry. Actually, we might take a look at chapter 4. Yeah, that's actually pretty nice. We might do a brief dive into chapter 4 soon. So anyway, second question is given for curves to describe all non-singular projective curves, which we haven't talked about yet, but we will. And a given birational equivalence class has a simple answer. As we've seen, there is exactly one. We have not actually seen this yet. We will see this. And then for the third question, we know that any curve can be completed to a projective curve by adding a finite number of points, so there is not much more to say there. And so as for the classification of singularities of curves, see chapter 5. While we're discussing the classification problem, I would like to describe another special case where a satisfactory answer is known, namely the classification of non-singular projective surfaces within a given birational equivalence class. In this case, one knows that every birational equivalence class of surfaces has a non-singular, and I think at this point we're hitting the point where we need to finish the rest of chapter 1. But basically, he goes through, and a lot of this stuff has to do with like how to get non-singular varieties or curves. And so then yeah. To study the intrinsic geometry on a variety, which we have not done in chapter 1, we will study divisors on a variety X, where a divisor is an element of the free abelian group generated by the subvarieties of codimension 1. We will define linear equivalence of divisors, and then we can form a group of divisors modulo linear equivalence called the Picard group of X. This is an intrinsic invariant of X. Another very important notion is that of a differential form on a variety X. This is something that we care about for our research. So using differential forms, one can give an intrinsic definition of the tangent bundle and cotangent bundle on an algebraic variety. So tangent bundle and cotangent bundle is when you take a maximal ideal and you mod out by the maximal ideal squared, and it leaves you with all of the linear terms in the space. And so basically like m quotient m squared gives you all of the things in the ideal of degree 1. And then similarly, of course, k over x quotient m over m squared gives you everything which is quadratic or higher. But yeah, then one can carry over many constructions from differential geometry, or like in our case, the Itali cohomology or de Rham cohomology theory, to define numerical invariants. For example, one can define the genus of a curve as the dimension of the vector space of global differential forms on the non-singular projective model. From this definition, it is perhaps clear that it is a birational invariant. And so then, perhaps the most important modern technique for defining numerical invariants is with cohomology. There are many cohomology theories, but we will be principally concerned in this book with the cohomology of coherent sheaves, which was introduced by J.P. Serre. Cohomology is an extremely powerful and versatile tool, Not only can it be used to define numerical invariance, for example, the genus of a curve x can be defined as the dimension of its homology at 1 as x as an extension of the localization at x. But it can be used to prove many important results which do not apparently have any connection with cohomologies, such as Zariski's main theorem, which has to do with the structure of birational transformations. To set up a cohomology theory requires a lot of work, but I believe it is well worth the effort. We will devote a whole chapter to cohomology later in this book, and we will basically be getting into that in Vakil now. Or not necessarily now, but like soon. It's a useful vehicle for understanding and expressing results such as the Riemann-Roche theorem. This theorem was known classically for curves and surfaces, but it was by using cohomology that Hizerbrüch and Grothendieck were able to clarify and generalize it to varieties of any dimension. Now that we have seen a little bit of what AG is really about, we should discuss the degree of generality in which to develop the foundation of the subject. In this chapter, we have worked algebraically over a closed field, but that is the simplest case. There are good reasons for allowing fields which are not algebraically closed. One reason is that the local ring of a subvariety on a variety has a residue field which is not algebraically closed, and at times it is desirable to give a unified treatment of properties which hold along a subvariety and properties which hold at a point. Another strong reason for allowing non-algebraically closed fields is that many problems in algebraic geometry are motivated by number theory, and in number theory, one is primarily concerned with solutions of equations over finite fields or number fields. For example, Fermat's last theorem is equivalent to the question, does the curve x to the n plus y to the n equals z to the n in projective 2 space for n greater than 3 have any rational points over Q? And so they need to work over arbitrary ground fields, which was recognized by Zariski and Vakil. In fact, perhaps one of the principal contributions of Vakil's Foundations book was to provide a systematic framework for studying varieties over arbitrary fields and the various phenomena which occur with the change of a ground field. Nagata went further by developing the foundations of algebraic geometry over Dedekind domains, which you guys can think of as basically well-behaved Noetherian topology. Or Noetherian rings. Another direction in which we need to expand our foundations is to define some kind of abstract variety which does not a priori have an embedding in an affine or projective space. This is especially necessary in problems such as the construction of a variety of moduli, because there one may be able to make the construction locally without knowing anything about a global embedding. And it goes on for a few paragraphs. One caution about working in extreme generality: there are many advantages to developing a theory in the most general context possible. In the case of algebraic geometry, there is no doubt that the introduction of schemes and sheaves has revolutionized the subject and made possible tremendous advances. We'll talk about schemes and sheaves pretty soon. On the other hand, the person who works with schemes has to carry a considerable load of technical baggage with him: sheaves, abelian categories, cohomology, spectral sequences, and so forth. Another more serious difficulty is that some things which are always true for varieties may no longer be true. For example, an affine scheme need not have finite dimension, even if its ring is Noetherian. So our intuition must be supported by a good knowledge of commutative algebra. So kind of putting all of this together to say, where does Blowup fit into all of this? Where do kind of rational maps come in? Well, really, we like to define these numerical invariants and discrete invariants of things by birational maps. And so a blowup is one very good example of a birational map, where if you can compute, the blowup of a variety that we care about in particular, that might prove something in terms of classifying like a cohomology theory on a certain variety, which in our case is the same thing as, actually computing the cohomology of something that we care about. So all of this to say, like it's pretty abstract. But how this is useful is like for smoothing out singularities and for saying what we need to add to a variety to get it to be a non-singular variety. And as Hartshorne has just kind of said, that's like the whole point. Okay. So enough exposition. Any questions? Okay. Cool. So if Y is a closed sub variety of affine n space passing through 0, we define the blowing up of Y. Wait, no. The blowing up at 0 of Y. There we go. To be squiggle Y, which is equal to phi. Nope, that was a terrible phi. Phi inverse of Y minus 0. Minus? What the hell is that notation? The important thing is that this works the way that it did for AN. I have no clue. Zero clue. Maybe because I'm posting these to YouTube now, maybe some poor bastard who watches all of these can go through and figure out what the hell this minus means. What? Okay. Where phi from x to AN is the blow up of AN at 0. So we're saying, okay, so phi inverse goes from AN to x. We're taking some subvariety of Y minus 0. And then what? Hold up. All right, Google time because Wikipedia might have the answer. Blow-up of a variety at a point. Well, that didn't help. Okay, Wikipedia was less help than Hartshorne, so well, I think maybe it means phi inverse send stuff to X. I think it maybe means pass it back to AN. Maybe they were trying to save space and say -1, -1. Because that makes sense. It sends it back to AN. Does that seem like something? But why not just say phi of phi inverse?
Maybe it's just a typo.
It seems pretty intentional. I don't know. Well, for whatever it's worth, so X is injective to AN times PI minus 1. This factors down to AN through phi. But then if we have a closed subvariety Y, and that should be injective. Closed subvariety of AN passing through 0. Then the blow up, this must mean I'm really struggling to put together a picture here. I'm just going to try something dumb here and reverse Google image search and see if anybody has posted to Math Stack Exchange. Okay. Okay. Nope, not inverse. This is a risky closure. I'm glad I checked that. Risky closure. Never would have guessed that. So take the inverse image of y set minus 0 and then take its closure inside the blow-up space. There we go. And really, I'll just start with y minus 0. I guess this is the Zariski closure of phi inverse. Goes to y squiggle, which is injective. There we go. That's our commutative diagram. Does this make sense? I wouldn't blame you if it didn't.
I feel if we keep going, it'll make sense as we work.
Okay. Yeah. So then the follow-up thing is to blow up any other P in AN. All we have to do is make a linear change of coordinates. So again, this is our whole idea of zeros not really preserved in affine space. So accordingly, y squiggle minus phi inverse of 0 is isomorphic to y minus 0. So phi is a birational morphism of y squiggle to y. Yeah. So any questions on this? So they have an example. So let y be the zero set of y squared minus x squared times x plus 1. This is called the plane cubic. We will compute, goodness. We will compute the blow up at 0 of y. So let T, U be homogeneous coordinates for P1. Then X, which is the blow up at 0 of y. Oh wait, no. At a squared. Is defined by xu is equal to ty. In A2 cross P1. And so basically for writing it twice. So for xy equals 0, 0 in A2, well, 0u is equal to 0t. Implies that w and t take on all real values in k. Right, and infinitely many solutions. And so 0, 0 is replaced by P1. And then this corresponds to the slopes of lines through 0. We call this P1 the exceptional curve E. Now, obtaining phi inverse of y in x by considering y squared is equal to x squared times x plus 1 and x equals 2y. So P1 has an open cover where t is 0 and u is 0. This was a this wasn't a W, this was a U. That. There we go. So letting without loss of generality t be non-zero, let t equals 1, and u as an affine parameter. Then y squared is equal to x squared times x plus 1, and y is equal to xu. And all of this is now in A3. Substituting, we get through xu squared is equal to x squared times x plus 1. And so then we get that x squared times u squared minus x plus 1 equals 0. And so we get two irreducible components. One defined by x equals 0, one defined by y equals 0, u arbitrary, which is E. The other defined by u is equal to x squared plus 1.
Tim, could you write out the steps with how you got to x squared times u squared minus x plus 1? Having a little
Oh, I subtracted, so it's x squared u squared minus x squared times x plus 1 equals 0.
Thank you. That makes sense now.
Yeah. And so taking xu to be 0.
Would it have to be negative x minus 1, not plus?
Where?
Last row. You distribute the minus.
You are absolutely right. Good catch. Thank you. So, So they say that E is defined by x equals 0, y equals 0, u in k, which gives us that xu is equal to 0, and then accordingly, if x is equal to 0, then we get 0 equals 0. And then the other is defined by u squared is equal to x plus 1, which makes sense. Oh, and then y is equal to xu. And this is y. And then these things meet at u plus or minus 1. So E intersect y at u is equal to plus or minus 1. Yeah. And so basically we can separate out the branches of E as things which are distinct between u ranging from minus 1 to plus 1. And just so it's clear, this is exactly the picture here that I drew. This is actually the example. So, yeah. So, any questions on this?
Nothing on my end.
Okay. So, I'm going to assign some homework because basically we should not move forward until everybody does some work on the stuff that we've done. So, I'm going to stop the recording because this is all the lecture content that I feel like I can really provide from Hartshorne. So I've annotated through 5 and 6. I have not done 1.7 yet. And so 5 is on non-singular varieties. Maybe I can do that one tomorrow. But 6 is on non-singular curves, and I have not done that yet. And so in as much as this really does not click unless you do some examples, I'm going to send an email with some homework in this, and then some homework in Vakil, do you guys have like 3 hours today to spend doing homework?
Around that.
Okay,
On call or independently?
just independently, whenever works for you.
Yeah, I think so.
Okay, so then I'll assign what I think would take me about 3 hours, and that will be probably 4 or 5 problems. Um, but feel free to reach out for help because I've done these problems. Um, yeah. So, okay, let me stop the recording. Thank you all for tuning in. And yeah, I guess.